Good afternoon and welcome to today's presentation, Helpful Information for Attorneys when Working with Forensic Engineers. In today's webinar, Dr. Iezzi will discuss what forensic engineers do, analytical tools used by forensic engineers, and examples of cases that use these analytical tools and techniques. To give you a little background about our presenter, Robert Iezzi, he's an accomplished expert witness and technologist with an outstanding record of achievement in chemical research and development. He has experience in product liability and patent infringement. Dr. Iezzi has worked in R&D and Fortune 500 companies for 48 years to develop expertise in paints, plastics, metal coatings, corrosion, pretreatments, fluoropolymers, nanotechnology, polymer science, and more. Attendees who require a passcode for today, the word is engineer. During the question and answer session, we ask that you enter this passcode into the Q&A widget for CLE reporting purposes. The Q&A is located to the left of your screen. Please remember that if you are applying for CLE credit, you must log onto your computer as yourself and stay for the full 60 minutes. You are also required to complete the survey at the end of the program. Please note that the CLE credit cannot be given to those watching together on a single computer. Tomorrow morning, we will send out an email with a link to the archived recording of the webinar. The slides can be downloaded from the resource list to the left of your screen. Thank you all for attending today. Dr. Iezzi, the presentation is now turned over to you.
Okay, thank you. Good afternoon, ladies and gentlemen. Thank you for attending my webinar. My purpose of this session is to provide some helpful information that you can use when dealing with the forensic engineers that you may retain as expert witnesses. What I'm going to cover today is an overview of what forensic engineers do and the various types of analytical tools they commonly use to provide value to attorneys as expert witnesses. I will cover 13 frequently used analytical tools, focusing mainly on the type of information each provides. I will also discuss 3 case studies where I have personally used these tools while serving as an expert witness. Then I'll do a very brief summary. First of all, what do forensic engineers do? Well, it's quite straightforward, actually. Forensic engineers identify what went wrong, why it went wrong, and how it went wrong. An absolutely critical aspect of this analysis that a responsible forensic engineer and expert witness provides is that their results, conclusions, and opinions must be unbiased, accurate, and defendable, even during vigorous cross-examination by opposing counsel and/or by Daubert or Fry challenges. Now let's dig into the various analytical tools that a forensic engineer can use. I should mention that this webinar is not intended to be a technical treatise on how these sophisticated, complicated instruments work, but rather provide information on the various techniques that they can provide and what you, as top-flight attorneys, can request from experts. Also, the webinar is not meant to be inclusive of all types of analytical techniques available to forensic engineers. Time simply would not permit that. Rather, I focus on the most common tools that I personally use in my expert witness and consulting practice in corrosion, paint coatings, metal coatings, chemical pretreatments applied prior to the application of paint or metal coatings, and plastics. Of course, the first step in any forensic engineering analysis is to simply examine the sample under a magnifying glass. This first step usually helps me determine what type of tests I need to do to obtain a broad picture of what went wrong. This slide and the next one list the various analytical tools I will discuss in this webinar. These techniques primarily involve the use of a microscope, hence the fancy name microscopy. I'll give you a moment to read these over. So here's the continuation of the list of analytical tools that I will cover today. I'll give you a moment to read those also. Note in the last two slides that there are many different techniques available to a forensic engineer. The choice depends on the type of information needed and the characteristics of a particular sample. It is very important to stress that most times I have to use 2 or 3 techniques that are complementary to best reach unbiased, accurate conclusions. For example, if I'm considering analyzing a plastic material, FTIR analysis, which is basically infrared analysis, might tell me the sample is either nylon 6 or nylon 6,6, which are 2 different types of nylon. Nylon 6 and nylon 6,6 have very similar FTIR spectra, and you can't tell the difference between the 2. But if I need to know the specific type of nylon, I can then use a technique called DSC, which stands for differential scanning calorimetry, which gives me the melting point of the sample. Because nylon 6 and nylon 6,6 have different melting points, I know if the sample is nylon 6 or nylon 6,6. Whereas with FTIR alone, I could not make that distinction. So that's a good example of the need to use complementary techniques to find out what I need to know. So let's now dive into each analytical tool. I'll start with optical microscopy. Optical microscopy is a fancy word for examining a sample under a light microscope, similar to evaluating a sample in high school biology or chemistry lab. You simply put the sample in its original or as-is condition on the microscope stage, that is, under the lens. There is no specialized surface preparation of the sample needed. Most scientific optical microscopes provide direct links to a camera and TV monitor to facilitate taking photos. And most have different light filters, such as polarized light, that provide sample contrast to see different features, such as crystallization in polymers, magnifications from 2x to 2000x are possible with a resolution of about half a micron. And note that a micron is 1/1,000,000th of a meter. So you can see very fine detail using an optical microscope. This is an example from my work using an optical microscope. This is a surface view, about 40x magnification, of a lead coating applied to copper sheet. The coating corroded in spots. The red corrosion spot shown was caused by a pore in the lead coating and is about 0.5 millimeter in diameter. Certain lead corrosion products are red. Optical microscopes are general-purpose instruments. I use them to document the original condition of almost every sample I analyze. Polarized light feature is very helpful in my work in determining the structure of plastics and why a plastic may have failed in surface. I'll next talk about the scanning electron microscope. I use the scanning electron microscope in most of the expert witness work I do. What I'm showing here in this slide is a high magnification micrograph of plant pollen. It's shown here just to demonstrate the extreme resolution capability of SEM. SEM produces images of a sample by scanning it with a focused beam of electrons. Electrons interact with the atoms in the sample, producing various signals that contain information about the sample's surface features. The resolution is better than 1 nanometer, and 1 nanometer is 1/100000th of a meter. And the SEM detects the outer few microns of a surface. So because SEM is so surface sensitive and has such good resolution, I often use it to determine what's on the surface of a material that may have caused paint to have poor adhesion and or fail on the surface. SEM can achieve magnifications of more than 500,000. That's about 250 times the magnification of the best optical microscope. Limitations of SEM are that samples must be fit into the sample chamber which is usually limited to about 6 inches maximum dimension. Samples must be placed in a high vacuum chamber for analysis, and samples must be electrically conductive. Non-conductive samples like plastic or paint must be coated with an extremely thin coating, usually gold, carbon, or platinum. Now, this thin coating is applied in the SEM itself immediately prior to the analysis being conducted. This is a photo of the SEM in a laboratory that I use frequently. It shows the SEM instrument and the scientist operating it. This is an example from my work. It involved the fracture of a metal handrail bracket. A lawsuit was filed when a handrail broke and the person fell down the steps. You're looking at a 500x SEM micrograph of the fracture surface. If you can see smooth facets there, I've indicated one with an arrow. The smooth fracture indicates brittle fracture, almost like a brick snapping in half. And the significance of the brittle fracture is that it indicates that the handrail bracket failed instantaneously, probably by having too much weight on it. I use SEM in nearly all my assignments because I get very high quality images of the original condition of the sample. It's also very cost effective, so I get very high bang for the buck for the customer. I'll next talk about energy dispersive X-ray spectroscopy, or also called EDS. EDS analysis is used in conjunction with SEM to get elemental analysis of what we're looking at in the SEM on a particular sample. EDS provides elemental results because the impact from the scanning electron beam on the sample produces X-rays that are characteristic of the elements present. The next slide, I'll show a sample Specter EDS. This is a EDS specter which shows elements at a particular location. Again, this is an example from my work. You can see high levels of lead. The symbol there is Pb for lead, and copper Cu, if you remember high school chemistry. So this is an extremely valuable tool that goes hand in hand with SEM. I get rapid elemental analysis on specific locations on a sample that is being analyzed while it's in the SEM. So EDS is also a very cost-effective analytical technique. I'll now talk about metallographic cross-sections. The metallographic cross-section I prepare by cutting a cross-section of a sample to obtain an edge view. This is analogous to cutting a steak on a grill to see if it's cooked to your liking. Then you mount the material, the cross-section material, in a plastic material. In the photo shown, the clear disc is the plastic mounting material. The thin but wide dark object embedded in the plastic is the sample that is to be analyzed. You then take that so-called metallographic mount and you grind and polish it using successfully finer abrasive particles to produce a scratch-free mirror finish. You then analyze the cross-section in the SEM or other methods that I'm discussing. Here's an example of my work. This is painted aluminum, which shows corrosion at the cut edge. The cut edge is shown on the left side of the micrograph. There you see the top coat, paint top coat identified, pretreatment layer identified, and then under that the corrosion products identified. On the right side of the micrograph, you see the primer identified and the aluminum substrate identified. And what this particular micrograph shows that the paint and the primer lifted off the surface along with the pretreatment, and you can see the corrosion product underneath the paint but on top of the aluminum, which actually forced the paint to lift from the aluminum surface. So I use metallographic cross sections frequently. They're very helpful for me in determining why coatings fail or why plastics fail, and also corrosion mechanisms. And I use the metallographic cross sections with SEM or some of the other techniques that I will talk about today. So far I've covered 4 of the tools that I use most often. I will now discuss some case examples of how I use these tools before I go back and cover the remaining tools. So let's talk about some case studies. Case study number 1 involves the corrosion of painted aluminum window and door frames. This particular case involved corrosion of aluminum extrusions, which I just mentioned. These aluminum extrusion door and window frames were placed in dozens of residential buildings in coastal areas, and they showed excessive corrosion and premature corrosion at cut edges of the window and door frame sections. My role as an expert witness was to determine why they failed so quickly, usually within a few years. Homeowners filed suit against who they bought the windows from, and the window seller sued everyone else: the aluminum manufacturer, the company that applied the paint, the window manufacturer, and the paint company themselves. This photo shows me doing paint adhesion tests on some of the samples that have failed. This photo is an example of the corrosion on a door frame section. Corrosion is about 2 to 3 inches from the edge, and abutting to the horizontal member. So you can see the corrosion extending there a couple of inches. Very severe, and made the homeowners very unhappy, obviously. This just shows the common type of paint systems used in industrial painting operations. You see the top coat paint, which provides the color, the aesthetics, ultraviolet protection, and perhaps some scratch resistance, chemical resistance. The primer provides mainly adhesion and corrosion protection. And the pretreatment layer, which is a very thin layer, which helps the paint stick to the metal surface. And the pretreatment layer also provides some corrosion protection. So if we think about those 3 layers in the next slide, you'll see what I'm making a point about the paint and the primer coming off the pretreatment layer. What I'm showing here is an SEM micrograph of a metallographic cross-section of the paint lifting from a cut edge. The cut edge is shown at the right, and the corrosion source at the right. The primer and top coat lifted from the surface together, as noted on the micrograph. If you look at the primer indication and top coat indication on the left of the micrograph, you see that the primer and the top coat lifted off together. And that means that the primer and top coat had good adhesion to each other, so the so-called intercoat adhesion is very good. So now that I've confirmed that the primer and top coat have good intercoat adhesion and are lifting off the surface together, but I still need to determine why. So let's take a closer look at the next slide, or a close look at the next slide to find out why. This is a higher magnification SEM micrograph, that's 2000x, of where the paint is just beginning to lift from the surface. I analyzed location C, and you can see it right in the middle of the micrograph. It's small, and it's a small c in white. And at that location C is where I used EDS, and I found out that that material at location C is the pretreatment layer. So it's clear to me that the paint was lifting off of the pretreatment layer. So the pretreatment corrosion, the premature corrosion, as I concluded, was not due to the aluminum substrate, was not due to the window manufacturer or the paint company. It was due instead to the poor pretreatment process by the company who painted the aluminum product, because the paint lifted from the pretreatment layer. Poor pretreatment layer was likely due to the use of tap process water, not deionized water, and or contaminated process water. And basically the root cause was poor process control at the company that did the painting. So you can see from this example how powerful the techniques of cross-sectioning a sample and using SEM along with EDS are. That is, three complementary analytical techniques. Case 2 I'll cover is the corrosion of copper roofing coated with lead. This project involved premature corrosion of copper roofing coated with a thin lead coating. Lead has been used in roofing and statues for centuries in Europe because it can last hundreds of years in most environments. Lead-coated copper is occasionally used on buildings in the United States because the lead gives a dull gray, antique look that is desired by some, and the lead should last decades. The lead is usually applied to copper sheet because lead is not very strong as a standalone material, and the copper substrate gives structural strength as needed, particularly for roofing. In this case, the lead-coated copper was used on a private residence because the owner wanted an antique look. Unfortunately, the lead corroded within 2 years, and the roof was a visual nightmare, with red and white corrosion products all over the roof. So much lead corroded and was washed off by rain that lead contaminated his lawn area and ponds, and he became a federal and state hazmat site and had his property monitored by federal and local environmental agencies. Needless to say, the owner was not happy and sued the contractor, architect, and the manufacturer of the lead-coated copper material. My role was to determine why the lead-coated copper corroded prematurely. Here's a photo of a small roof section. You can see the non-uniform appearance and the corrosion. I analyzed the circled section along with many other areas. This is an optical micrograph of the cross-section of that section that I circled in the previous slide. The most prominent feature is the large uncoated area, that is a pore, P-O-R-E, and thin coating on the side exposed to the atmosphere, that is the outer surface at the top of the micrograph. Note the other side on the bottom of the micrograph, which is the inner side, which is not exposed to the atmosphere, had a relatively uniform and thicker coating. Coating on the outer side was below the ASTM specification for coating thickness. The inner side was within ASTM specification for coating thickness. This sample was typical of the dozens of samples that I analyzed. This is an SEM photograph at 2000x of a surface view. It shows the pore in the lead coating where I've located and indicated as location A, and that location exposed some of the copper substrate. Location A was analyzed using energy dispersive X-ray spectroscopy, or EDS, and showed the copper substrate, which I'll indicate on the next slide. Here you can see the EDS spectra of a pore. Again, it's location A from the previous slide. And it shows the copper substrate. Again, the copper symbol is Cu. Lead tin intermetallic, which binds the lead coating to the copper, is also evident by the lead that's indicated in the micrograph. That is, lead is symbol is Pb, and the tin, which the tin symbol is Sn. There's some tin added to the lead so that the lead flows better and bonds better with the copper substrate. So my conclusions from this project was that the premature corrosion caused by porosity and non-uniformity of the lead coating. The porosity exposed the copper substrate, creating an electrochemical corrosion cell which accelerated the corrosion of the lead. The root cause of this issue was poor lead-coated copper manufacturing. The third and last case study that I'll talk about is the manganese phosphate coating. This project involved manganese phosphate pretreatment for air conditioner condensers. Manganese phosphate pretreatment is a thin coating applied to metals to help with lubrication of moving parts, particularly break-in periods. The most common example is for automotive engine crankshafts. Manganese phosphate is a crystalline coating. It's called a pretreatment because it's so thin. And this crystalline coating absorbs lubricating oil and holds it during the break-in period. Manganese phosphate coating itself has lubrication properties, so it and the oil provide temporary break-in lubricant. The problem occurred when the air conditioner manufacturer switched manganese phosphate chemical suppliers. With the new manganese phosphate supplier, premature failure of the condensers occurred very rapidly. The air conditioner manufacturer sued the new chemical supplier. I was called in as an expert in pretreatment chemicals to find out why the new manganese phosphate product failed. This slide shows a 200 magnification SEM micrograph of the surface of the original pretreatment that's shown on the right of the slide versus the one the air conditioner manufacturer switched to on the left. So the new pretreatment, the alternate pretreatment, is shown on the left. The original or current pretreatment is shown on the right. The current manganese phosphate pretreatment is seen to be very smooth and uniform. It had the appearance of a typical manganese phosphate coating. The alternate manganese phosphate was very rough, non-uniform, and porous. With this SEM information and extensive laboratory testing of both manganese phosphate chemicals, I was able to determine that the non-uniform, porous manganese phosphate coating wore away critical components of the condenser seals at an accelerated rate, causing the air conditioner compressor to lose pressure and not be able to pump refrigerant. This slide has an SEM micrograph, 200x, of a different area of the compressor component with the alternate manganese phosphate coating. That is, the new manganese phosphate coating. Note the non-uniform manganese phosphate crystals and the areas with no manganese phosphate coating at all. I've indicated those with the arrows and the caption showing at the top of the micrograph. These non-coated areas were also rough and contributed to the premature seal wear and compressor failure. So this premature failure of the compressors was due to the alternate or new manganese phosphate coating supplier. The new manganese phosphate coating was very rough, very non-uniform, and porous. And that roughness wore away the compressor seals at an accelerated rate, causing the compressor to lose pressure and not pump refrigerant. I'll next talk about some of the remaining analytical tools. I'll talk a little bit about something called confocal scanning optical microscopy. Confocal microscopy is relatively new, about 20 years old. The biggest advantage over other types of microscopes is that it gives excellent images of three-dimensional surfaces, such as a sharp bend on a sample or sample with a very rough surface. The other types of microscopes which I discussed so far today usually only detect features on a flat portion of a sample. The non-flat portions of the sample will not be in focus. Other advantages of confocal microscopy is that no sample preparation is needed, and you can get quantitative measurements and visualization of the surface roughness by just putting the sample underneath the microscope lens. Here's an example of the tremendous resolution that's possible of the as-is surface. We are looking at a small section of a €1 coin. The section is about 800 microns square. So that section that we're looking at is about nearly 1 millimeter square. The top of the star raised about 30 to 50 microns from the flat area of the coin. You can tell the raised area thickness by the color difference from red to blue and the associated color scale bar on the right. The dark red on the scale bar on the right is a baseline of 0 microns. Dark blue gives a depth from the top of the star at about 50 microns. So confocal microscopy is very useful in determining the surface roughness of a sample that may have failed in service or identifying a manufacturing defect. So here we're looking at a sample difference of about, the thickness difference of about 30 to 50 microns. Remember, a micron is a millionth of a meter. So I use confocal microscopy when I need extreme detail about the surface features of a sample. I use it rarely because very few labs have this equipment, and the cost per sample is very high. And I'll talk a little bit about atomic force microscopy. Atomic force microscopy provides visual images with atomic resolution of surface features. AFM is capable of quantifying surface roughness of samples down to the nanometer scale, and a nanometer is 1 billionth of a meter. This is an example of the extreme surface sensitivity of AFM. Looking at the surface of a sample, it's hard to read the vertical bar on the right, but the red is about 1/10 of a nanometer, and the light yellow is about 2/10 of a nanometer in thickness. So we are measuring a surface roughness difference between the red and the yellow of about 1/10 of a nanometer. So that surface difference is about 1/10 of a billionth of a meter. So as you can see, AFM is a tremendous tool for surface characterization. I use AFM when I need extreme detail about the surface features of a flat sample. And I use confocal scanning microscopy when the surface is not flat. Coincidentally, I just read an article in Chemical and Engineering News, which is a technical journal, and it indicated that the 3 scientists who invented AFM in the 1980s have been awarded a $1 million prize by a scientific group in Sweden called the Kavli Foundation. 3 inventors share a $1 million prize from Kavli in nanoscience, because AFM's role in the development of nanotechnology has been instrumental in the rapid development of nanotechnology as a science and as a practical engineering material. And I'll talk about X-ray photoelectron microscopy, or XPS. XPS provides a type of information on chemical compounds that is present on the surface of a sample. Most other techniques that I spoke about today give only elemental analysis, but XPS gives chemical compound information. And by that I mean other techniques I identified today might identify sodium and chlorine, but XPS will tell me if the sodium and chlorine are chemically bound as salt or some other compound. The XPS spectra that I'm showing in this slide is an example of various moisture components on a sample surface. The technique works by measuring the binding energy of a material. Using this information, the binding energy, I can determine in this particular case if a contamination of a surface prevented good paint adhesion, and if so, the specific composition of the particular contamination. So I use XPS when I need to know the chemical compounds that are present on the surface at the top 10 nanometers of the material. And it tells me the compounds, not just the chemical elements. So obviously, XPS is an extremely surface-sensitive technique. Next, talk about transmission electron spectroscopy. TEM, as it's called, provides an image of a material by shooting beams of electrons through an extremely thin sample. TEM gives extremely fine detail of a material, and you can get image resolutions of about 1/10 of a nanometer. TEM gives better images than SEM, or optical microscopy, but requires much more sample preparation, mainly from cutting the very thin samples using a technique called microtoning. As an example, here are TEM images of molybdenum compounds. Photo D in the bottom left clearly shows rod-like structures about 10 nanometers in diameter. This image gives an idea of the level of detail that is possible using TEM. I use TEM in cases where I need extreme details of the material structure, perhaps failure analysis of an automotive axle that broke and caused an accident. It helps me determine why did the axle break. So TEM provides extremely fine detail, even as small as a single column of atoms, which is thousands of times smaller than the smallest resolvable object in a light microscope. I use it rarely because I usually do not need details down to the atom size. TEM is more suitable for basic material research at the atomic level. Sample preparation is tedious, and that very thin samples are needed to transmit electrons through it. Very few labs have TEM, and it's high cost per sample. And TEM is typically overkill for most of my work. So we'll take a break.
Okay, if all the attendees could type in the passcode, we will start with our first question. I have heard of some experts using NMR in their work. Have you ever used NMR, and if so, what does it tell you that the other analytical tools you described do not?
NMR stands for nuclear magnetic resonance, and it's a technique that identifies the chemical structure of a polymer. Polymer, of course, being a paint or a plastic. And it does that identification on a molecular level. I have not used it in my work because I have not found it necessary to determine that level of detail. Infrared techniques such as Ftir analysis will tell me the type of polymer I am working on, and that is usually sufficient for what I need as a forensic engineer. NMR is more appropriate for basic research into new polymers or in medical research. Also, NMR is an expensive technique, and not a lot of laboratories have that particular piece of equipment. Any other questions?
Yes. You mentioned degree of crystallization in a paint. What is that?
Degree of crystallization is best explained by considering spaghetti. Plastics or paints can have an amorphous or crystalline structure. Amorphous means the polymer chains have no set order or structure, similar to cooked spaghetti. Crystalline means the polymer chains have a set, rigid structure, similar to holding a handful of uncooked spaghetti. Most paints and plastics are semi-crystalline, meaning that they're partially amorphous and partially crystalline. The amount of crystallinity can have is called the degree of crystallinity, and the degree of crystallinity has a significant effect on the mechanical properties such as flexibility and strength of the paint or plastic. So it's sometimes necessary to know the amount of crystallinity or so-called degree of crystallinity in the work that I do in plastics and in paint coatings.
Great. Can you talk about forensic engineering and construction site accidents resulting in personal injury?
Yes, somewhat. I've worked on a few construction cases as a forensic engineer. Most of them were involved in corrosion of components, primarily the components that would be exposed to the atmosphere, primarily painted windows and door frames, painted railings, or even non-painted railings, metal railings. The structural aspects there is that if they fail, they would be more prone to let water enter the structure. They would be prone to let air enter the structure, and in certain parts of the country, that's catastrophic. I've worked recently on a couple of cases in hot, humid environments in high-rise buildings right on the seacoast, where these materials were corroding very rapidly within 1 or 2 years, and water was entering the building, and also a lot of moisture just from the humidity in the atmosphere.
Thanks, Bob. If you can continue on, that'd be great.
Okay, be glad to.
Thank you.
Yep, my pleasure. Next, talk about Auger electron spectroscopy. Auger electron spectroscopy is excellent for showing a visual image of the chemicals and elements on the surface of a material. This particular slide is an example of what Auger spectroscopy can do in helping me as a forensic engineer. I can visually see how the chemicals elements are distributed on the sample surface, which is a very powerful tool in explaining my results to a judge or jury. This particular sample compares the elemental images to the SEM image on the left. So the SEM image on the left shows a surface defect. The middle photograph shows the Auger image of the same spot for the element indium. The right photo shows the Auger image of the same spot for selenium. Therefore, we learn from this that the sample defect is composed of a combination of indium and selenium. This is very useful in microelectronics type of work. So I use Auger spectroscopy when I need visualization of the spatial distribution of the chemical elements on the top few atom layers of a sample surface. This is ideal for metals, but polymers may degrade during analysis, so one has to be very careful when applying this to polymers, such as paints or plastics. Very few labs have this equipment, and it's somewhat costly to run per sample. I'll next talk about infrared spectroscopy, particularly this technique called Fourier transfer infrared spectroscopy. Fourier FTIR helps me identify surface contamination that may contribute to a product failure. It provides chemical analysis, particularly by identifying organic materials, plastics, lubricants, adhesives, and cleaning agents. And it's ideal for direct in situ analysis of organic contaminants on metal surfaces. So again, that's very helpful when I've got a paint adhesion issue to metal. FTIR can help identify what type of contamination might be contributing to that, be it oil that was not removed prior to the painting step. If it's a plastic part, there could be drawing lubricants that would be on the plastic part to help draw the part. Many times these lubricants or oils are difficult to remove, and if they've been on there for a long period of time, they tend to oxidize and become extremely difficult to remove. I'll show an example in this particular slide. This is an example of an FTIR spectrum. FTIR analysis is like comparing fingerprints. You compare the sample spectra, and that's shown in this slide in the bottom spectra in blue, to a reference spectra that matches the sample. The reference spectra here that matched would be the top spectra, noted in red. Computer software does the matching for you, so it's a fairly straightforward technique and very easy to interpret the results. This particular sample, the blue sample, compared very close to the red standard for polystyrene, so it was reasonable to conclude that the material that I was analyzing was indeed polystyrene. So I use FTIR frequently for chemical analysis of organic materials, be it paints and plastics. It's a fast, inexpensive test, and most chemical labs have FTIR. Another common chemical technique that I use is gas chromatography, mass spectrometry, GCMS. It's a mouthful, which I stumble with occasionally. GCMS quantifies organic volatile materials like oils and greases. The GC component separates mixtures into individual components. Then the mass spectrometry component identifies the various compounds by comparing to reference databases. The other techniques I covered today deal with solids only and cannot analyze liquids and gases, whereas GCMS is very effective for identifying different liquids and gases, in addition to solids. How do I use this? Frequently for chemical identification of volatile compounds, solids and gases primarily, liquids and gases primarily. Examples would include outgassing of plastic food containers or can coatings. That would be outgassing of the coating or the plastic into the food product itself. I can also detect composition of chemical fumes, composition of dangerous vapors that might be in the air, like explosive mixtures, things like that might be in the home. This is a fast, inexpensive test, and most chemical labs have GCMS capabilities. Next technique I'll talk about, sorry, I've already missed a slide there, pardon me. Next technique I'll talk about is X-ray diffraction. X-ray diffraction identifies crystalline materials. It enables quick phase identification for a large variety of crystalline samples. It provides information on structures, phases, preferred crystalline orientations in materials, average grain size, crystallinity, and crystal defects in a material. So this is very, very helpful in determining why materials might have fractured in grain boundaries and other locations. Helps also determine if you get brittle fracture or ductile fracture, which can help explain the failure mechanisms of materials as they fail. So as I mentioned, it provides crystalline characterization. I use X-ray diffraction to mainly identify compositions of metal samples. That is it brass, is it copper, is it steel, is it zinc, is it whatever. I also use X-ray diffraction to determine the degree of crystallinity of plastics and coatings. As I mentioned before during one of the questions, degree of crystallinity determines the mechanical properties of plastics and paints. Mechanical properties such as strength, flexibility, and toughness. And the degree of crystallinity has a significant effect on these properties in a paint or a plastic. X-ray diffraction is a fast, inexpensive test to run. The last analytical tool I'll discuss is X-ray radiography. This is basically X-ray. It's basically the same as when you get X-rays of your body. It's an imaging technique that uses X-ray radiation to view the internal structure of an opaque object. The X-rays pass through the object that are captured, and the X-rays are captured behind the object with a detector. Here's an example from my work. This X-ray showed that there were no cracks in the metal handrail bracket that I described earlier in this presentation. And by showing that there were no cracks several slides ago, this particular job, I was able to demonstrate that the bracket itself was not at fault. So how do I use X-rays, radiography? I use it occasionally to determine if cracks are prevalent near a corrosion or a product failure site, and if the cracks contributed to the particular issue. So now I'll move into a summary, a few slides of summary, and I'll briefly go over the 13 techniques that I used. Optical microscopy, and again, this is a summary slide of what I've discussed today. That's useful for documenting the original condition of a sample. I can usually get magnifications up to 2000x with very good resolution. The scanning electron microscope, or SEM, that gives me high quality images of as-is surfaces, and I can go up typically to about 500,000 magnification. EDS, or energy dispersive X-ray analysis, gives me elemental analysis of the surface. This is used in combination with SEM, and the EDS is usually an attachment on a SEM instrument that can give that analysis very quickly. And as I've showed in a couple of examples, it's very useful. If I have a particular spot in the SEM image and I want to know what the elements are, I can focus in on that particular spot and determine the particular elemental analysis with EDS. The Metallographic cross-section technique I talked about. It's like cutting a piece of meat on a grill to see if it's done. Basically, you get an edge view of the sample. So I frequently cut up plastic samples or paint samples to get an edge view to determine the mode of failure, why it failed, how it failed. And that's a very powerful technique used in combination with some of the other techniques that I've talked about, such as optical microscopy, SEM, or any of the other microscopic type of techniques. AFM, atomic force microscopy, that gives me surface features on an atomic scale, extreme surface detail, and can really detect surface roughness to the most minute scale imaginable. The example that I showed there, it was able to detect surface roughness differences of 1/10 of a nanometer, which is 1/10 of a billionth of a meter. So you can just imagine how small and surface sensitive AFM actually is. XPS, X-ray photoelectron spectroscopy, that tells me information on the chemical compounds on the surface. Like I described earlier, many of the techniques that I talked about only give elemental analysis, whereas if I need to know the particular chemical compounds of those elements, then that will help. Another example might be elemental. I might get hydrogen, sulfur, and oxygen, whereas XPS might tell me that hydrogen, sulfur, and oxygen is combined as sulfuric acid as H2SO4. So XPS is a very, very powerful chemical tool. The other techniques, confocal microscopy, this provides analysis of a non-flat surface. So that's very useful if I want to look at a very, very rough surface and see the entire surface. And also if I have like a sample that is bent, say a 90-degree bend, and I want to look at extreme surface detail right at the apex of the bend, the confocal microscopy will be very helpful in doing that. TEM, transmission electron microscopy, is useful for extreme detail, usually on the atom scale. And as I mentioned, that's usually more suitable for basic research at the atomic level. AES, Auger electron spectroscopy, gives me a visualization of the chemical elements on the top atom layers of a particular material. FTIR, Fourier transfer infrared spectroscopy, tells me chemical analysis of organic material. GCMS, chemical analysis of volatile materials, particularly solids and particularly liquids and gases, X-ray diffraction, compositions of crystalline material, and X-ray just internal cracks or defects. So as a final summary slide, forensic engineers have many technically advanced analytical tools at their disposal. Each tool has its own unique capability to help determine why a product failed. Many of the tools are complementary. Frequently, more than one tool is needed to get the whole story, to produce unbiased, accurate results that are defendable in court. And it is to the attorney's advantage to be aware of these various tools and capabilities to maximize the value of an expert to the theme of the case. So I'll try to answer any questions that you may have. My contact information is listed here. If you wish to contact me after the webinar or in the future with questions, I'll try to answer them if I possibly can. My primary areas of expertise are corrosion, paint technology, metal coatings, pretreatments for metals and plastics, and plastics themselves. So with that, I'll try to answer any questions that you may have in the 3 or 4 minutes that we have remaining.
Thanks, Bob. If all the attendees could type in the passcode again, that'd be perfect. Bob, we have a question with regard to the course of study to become a forensic engineer. Is there a subspecialty that relates to the biomedical field?
Well, I think biomedical engineering is certainly a strong field, would be ideal for becoming a forensic engineer in that particular area. Also, many of the top-rated universities would have cross-fertilization type of curriculum where, say, a biomedical engineer could take a lot of material science courses, which I think would be very, very helpful in becoming a forensic engineer also. As you can see, a lot of the techniques that I talked about are from the material science area, and I have my PhD in material science. Also, chemistry courses, particularly analytical chemistry courses, would be very useful in becoming a forensic engineer. As you could see, a lot of the techniques I use were also chemically oriented, and even though I never took an analytical chemistry course in college, working in the chemical industry for over 40 years in research and development, I had to use these techniques to effectively perform the functions of my particular position.
Bob, you talked about a lot of sophisticated instruments. Do you know where we can find such equipment?
Yes, there are several labs that have the equipment, depending on the type and depending on the level of sophistication of the instruments. I can give you, as an example, there are several test labs around the country that have many of the more commonly used techniques, such as FTIR, SEM, EDS, X-ray diffraction, and some of the high-powered optical microscopes. Most labs have those, and I'm in the Philadelphia area, and I have 2 labs within 45 minutes of me that have almost every single technique that I want to use. And most big cities would have that capability also, I would think. Some of the more specialized instruments like AFM, atomic force microscopy, AES, Auger spectroscopy, and TEM, they can be found in highly specialized test labs, but you got to dig pretty hard to find those. More commonly, you'll find those at research universities. Places like Lehigh University, very strong in this type of characterization. University of Pennsylvania, Drexel. These are just universities in the Philadelphia area where I would go when I need to find the instruments that I cannot find in a test lab. I typically like to work with a test lab for 2 reasons over a university. Number 1, the test lab, I can get faster response. And number 2, the test labs are geared to dealing with industrial problems and industrial people like myself. Whereas some of the university test labs, you have to wait to get analysis, takes a while, and also the cost can be very high relative to an industrial test lab because the universities have a pretty significant overhead typically 25 to 45% overhead that they have to mark on up to every sample. So that gets costly to attorneys and to ultimate clients.
Okay, this is our last question, Bob. What geographic areas have greatest demand for forensic engineers?
I cannot say if I think there is a greater demand. Clearly, I do work all around the country, and the cases that come in from everywhere and anywhere, the most rural areas and the most populated areas. With that said, perhaps the bigger cities, I get a lot of work out of New York, get a lot of work out of Los Angeles, a lot of work out of Chicago, a lot of work out of Dallas and Texas. So perhaps a little more in the bigger metropolitan areas because there's more people there, there are more lawyers there, and there's more people filing lawsuits there.
Okay, great. Thank you so much, Bob, for your presentation and preparing this webinar for us. And thanks to all the attendees who took time out of their day to be on the webinar with us today. If you would like to speak with a TASA representative regarding an expert witness for a case that you are working on, please contact TASA at 1-800-523-2319. We also had one of our colleagues sitting in today for purposes of listening in on the webinar. So Tom Masucci will be giving you all a phone call just to follow up on the webinar today. In addition to being your best source for testifying and consulting experts for the past 60 years, TASA also offers e-discovery and forensic solutions, free interactive webinars, cybersecurity services, day-in-the-life videos, in addition to research reports on expert witnesses, like the Challenge History Report 2.0, Professional Sanction Search, PSS, and the Expert Profile 360. At the end of this presentation, we will have a survey that will pop up on your screen. We ask that you fill that out, and you will receive a follow-up email tomorrow morning with the archived webinar and the presentation that was used by Bob. If you have any questions, feel free to email us. This concludes our presentation today. Thank you.